I can just do it here. So in the best case, right, we're doing one recursive call, and basically we're splitting the array in half, right? Remember the diagram I just erased? We're just passing in the first half of the array. So that's kind of generalizable to every case, right? Every level. So we're passing in n, then we're passing in n over 2, we're passing in n over 4, and etc. We're halving the size of the array at each recursive call. And so the height of this tree is going to be log n for the same reason as it was above, okay? And then the branching factor is going to be 1. We're just having one recursive call. And the amount of work is now what we need to figure out. Okay, so notice that it's really just linear in terms of whatever is passed in, right? It's really equal to the size of the array that is passed in. And so we can say that this is just theta of n, but I don't really like to say that it's n because n is not applicable to every level of our recursion tree, so I just say it's linear. So now it's really just plug and chug. So I equals 0 to the height, which is log n. Branching factor is 1, so again, I'm not going to write that. And then the amount of work is linear, and so that's going to be n over 2 to the I. And actually, this is the exact same formula up here, right? And we know from there that it's theta of n, so we can just say that the best case is theta of n. Okay, so that was simple enough. Now what about the worst case? The worst case is when we make 2 recursive calls, right? And so in that case, we have n making n over 2, n over 2. We have each of them making 2 n over 4. Okay. And then each of them is making n over 8, and so on and so forth until we get down to 1. The height doesn't change here, right? The number of nodes is definitely larger, but the height is still the same because the way that we decrement for each level stays the same. So height is still log n. The branching factor is 2 now, right? We're making 2 recursive calls. And then the amount of work per node is really still the same, right? We're still doing a linear amount of work per node, right? Because the linear amount of work per node is coming from this for loop, and that's not affected by this random coin value, right? So again, it's plug and chug. So I equals 0 to log n, 2 to the I times n over 2 to the I. We'll notice that this really nicely cancels out. And so we have this summation from I equals 0 to log n of n, which is really just log n times n, or better put, n log n. Okay, and so that is our worst case. So our best case is theta n, worst case is n log n. Great. So let me just erase this for now. That up here. Okay, and now let's look at this one. So this is making 2 recursive calls no matter what, so we can automatically assume that the worst case and the best case are going to be the same. And notice that we're now passing in n-1 and n-1 instead of halving the array or the input size, right? So our recursive tree is going to look something like this. Right, and so each of them is going to make 2 calls until we get down to 1. So what is the height of this tree? The height is actually n, right? Because at each level, we're just decrementing the input size by 1 until we get down to 1. The branching factor is 2. And now the amount of work we do is really just constant, right? Because all we're doing is just doing these recursive calls and nothing else, apart from the base case, obviously, but we only care about the recursive case. So the amount of work is just constant. And so again, plug and chug. So I equals 0 to, now I'm putting n-1 instead of n because indexing from 0, if you want n number of things, you would end up at n-1 index. But it doesn't really matter if you put n. And then 2 to the I times theta 1, right? Which is really just I equals 0 to n-1 of 2 to the I. And this is conveniently one of the formulas that was up above, right? Specifically the second one. And this ends up in 2 to the n minus 1. 2 to the n minus 1, which is really just theta of 2 to the n. So this is an exponential runtime, both best case and worst case. So this is a really horrible function. But how do you actually calculate this, what this is, very mathematically? Well, you could again employ the same formula as the geometric series, right? So one thing that you can do is, let's say that so let's try plugging it into the geometric series. So it's going to be, if I just expand out this summation, right, it's going to be 1 plus 2 plus 4 plus 3 plus all the way to 2 to the n minus 1. Okay. And then remember that my summation is going to be a1, which is 1, times 1 minus r to the n minus 1 over 1 minus r, right? So my r is 2 in this case, 1 minus 2 to the n minus 1 over 1 minus 2. And then 1 minus 2 is negative 1, so basically I can just flip the signs in my numerator. So 2 to the n minus 1 minus 1. And because n minus 1 is basically n, right, I can just say that this is equal to 2 to the n minus 1. And if you're not convinced that we can just simplify the exponent like that, notice that 2 to the n is really just 2 times 2 to the n minus 1. And this constant factor is always negligible. Okay, so anyways, we get 2 to the n minus 1, which is exactly what we got here. So that works mathematically as well. All right, so here the best case and the worst case was 2 to the n. Okay, and then last but not least, this is a little bit tricky. So feel free to skip this one. But as an extra practice, if you look at this function, it's kind of unique because you're calling recursively n number of times, right? That's like a huge blow up in our recursion tree. So if we actually draw what's happening, we have n at the top, and then this is going to be calling, let me draw it out a little bit better. This is calling n minus 1 n times, right? So this whole thing is n, or capital N. And then each of them is calling n minus 2 n minus 1 times, right? So basically whatever this n is, whatever their input size is, it's going to call n minus 1 n number of times. So that's going to be a huge blow up. So actually our height is amazingly still n, right? Because our height is just dependent on how we're decrementing from one level to the next level, which is still the same concept as in the above problem. But now our branching factor is huge. And so if we look at what our branching factor is, this is really just hard to, I guess, derive it on your own, but it is doable for sure. So again, let's let I be the level that you're on. So if I is 0, right, which is the root, then you have n factorial over n factorial, which is really just equal to 1. And that's true, right? You only have one node at the 0th level. Now, if I is 1, if you're at the second level, then you have n factorial over n minus 1 factorial, which is going to equal n, right? So really, this is referring to the branching factor at each level based on this n factorial is, think about it as you go down to more and more levels, the amount of nodes you have per layer, per level, is really just equal to n times n minus 1 times later on n minus 2 times n minus 3, etc. Right? So that's going to result in some kind of a factorial. And so this is how it's going to be derived. Okay, and then the amount of work per node is actually going to be n, linear. And the reason for that is because we're just counting the number of iterations of this for loop. And again, we just ignore what we're doing inside the for loop because this is a recursive call that we're already taking care of. And so this is really just linear. So if you put this all in terms of summation, then you have I equals 0 to n. The branching factor is n factorial over n minus I factorial. And then the amount of work is linear. And remember that at the ith level, our our amount of work is going to be n minus I. And so, yeah, so that is, sorry, I was thinking, did I do it incorrectly in 1.3? But I think I did it correctly. Okay, so for 1.4, back on track. So this is going to be the formula. And then if you basically simplify, you can basically cancel out the n minus I in the denominator and the n here. And so that's going to result in I equals 0 to n factorial over n minus I minus 1 factorial. Okay, now this seems really complicated to solve, and you would be right. So again, another trick that we can employ, like we did in the first problem, is making a much simpler expression by using an upper bound, right? So in this case, this is going to be less than or equal to the same summation, but now just n factorial, right? We're not even dividing this by anything, in which case it has to be greater than or equal to what we had here originally, right? So this bound makes sense. And so now we can easily simplify this because n factorial doesn't depend on any I. So really we just have n times n factorial, which actually amazingly is the answer. And we can say that this is O of n times n factorial. Okay. All right. So I guess you can process that a little bit more. I think the hardest part for me was coming up with the branching factor, right? Realizing that the branching factor in this case is actually variant depending on the level that you're at, whereas in all the previous problems, it was fixed for all nodes, right? So here you had to determine what your branching factor is by multiplying the branching factor at all the nodes, at all the levels, sorry, at all the levels above you. Okay. All right, and then the reason you do n factorial over n minus I factorial is because n factorial is really just like the entire multiplication of all the levels in your tree, right? But then the n minus I factorial is just going to give you how many nodes you have in your level. And so that's going to be the number of nodes. Really, it's just the number of nodes per layer. Okay. So hopefully that made sense. I'm going to be going over the next part of this review in the next video.